Imagine sending light through a cloud of atoms and detecting a photon on the far side. How long did that photon spend stored inside the atoms?
The answer might be extremely short, but it still has to be 0 or a positive amount of time.
That is the natural assumption. Yet this experiment found conditions where the measured answer was negative.
Negative time? Did the photon leave before it arrived?
Not in the everyday stopwatch sense. The experiment did not film a photon traveling backward. It measured the atomic excitation time associated with photons later transmitted.
So it asks what happened inside the material, but only for photons that successfully came out?
Exactly. The paper is titled Experimental Observation of Negative Weak Values for the Time Atoms Spend in the Excited State as a Photon is Transmitted.
That sounds like a precise accounting problem.
It is. When resonant light enters an atomic medium, some energy can temporarily appear as atomic excitation. The researchers asked whether the integrated excitation, conditioned on transmission, matches the photon's group delay.
And group delay can become negative near an atomic resonance.
Yes. The question was whether that negative number was merely caused by pulse reshaping, or whether an independent measurement of the atoms would return the same sign. Separate two outcomes. A photon can be scattered away, or it can continue through the cloud and be detected as transmitted.
If an atom becomes excited, I would associate that with absorption and scattering. So transmitted photons should produce almost no excitation.
That is one plausible story. Another is that a transmitted photon interacts coherently with the cloud and creates excitation before its energy is emitted forward again.
What was the baseline?
The researchers called it tau 0, the average atomic excitation time without selecting a final outcome. It is the time integral of the expected number of excited atoms. Semi-classically, it equals the scattering probability multiplied by the atomic lifetime.
But they wanted tau t, the excitation time specifically associated with transmission.
Right. The initial condition is an incoming photon, and the final condition is that it crossed the medium without scattering.
Is that where a weak value enters?
Yes. A weak measurement disturbs the system only slightly, and post-selection keeps runs with the chosen final result. A weak value is not restricted to the ordinary range of the observable.
So, although the expected number of excited atoms lies between 0 and 1 for a single photon, the post-selected weak value can be negative.
Precisely. Theory predicted that the integrated weak value for transmitted photons equals their group delay, even when interference makes that delay negative. This experiment tested the prediction across different pulse widths and optical depths. The team prepared cold rubidium-85 atoms at roughly 60 to 70 microkelvin. The cloud was about 1 millimeter long, and the relevant excited state lifetime was approximately 26 nanoseconds.
How did they monitor such a brief excitation without strongly disrupting it?
They used two beams. A pulsed signal beam was resonant with the atomic transition and produced excitation. A continuous probe beam traveled the opposite way and was detuned from resonance.
What did the probe reveal?
Through a weak cross-Kerr interaction, atomic excitation changed the probe's optical phase. The phase shift served as a gentle readout over time.
But the signal pulses contained about 100 photons on average, not exactly 1.
Correct. Coherent pulses provided faster data collection. After the cloud, the signal was heavily attenuated and sent to a single-photon detector. The team compared the probe phase in shots with a detector click against shots without one.
Subtracting those averages isolated the extra phase associated with one transmitted photon?
That was the method. They tested Gaussian pulses with root mean square durations of 10, 18, 27, and 36 nanoseconds. They varied resonant optical depth around 2 and 4, with depth around 3 for the 36 nanosecond case.
Could they see the effect in one run?
No, the expected phase shift was only about 10 to 20 microradians, while phase noise was around 120 milliradians. One parameter set required tens of millions of atom cycles and roughly 10 hours of data collection.
So the answer came from averaging a tiny correlation.
Yes, for each setting, they built a phase shift trace and integrated the relevant region to obtain tau t divided by tau 0. The measurements changed from positive to negative as the pulse became more narrowband, matching the predicted change in group delay.
What were the clearest numbers?
For the most broad-band pulse, the mean excitation time was 0.54 plus or minus 0.28 times tau 0. For the most narrow-band pulse, it was negative 0.82 plus or minus 0.31 times tau 0.
So the sign really reversed. The transmitted photon condition produced a negative integrated probe response.
Exactly. For the 10 nanosecond pulse at optical depth near 4, the measured ratio of 0.54 plus or minus 0.28 agreed with the theoretical value of 0.45.
Did every setting match perfectly?
No, the overall pattern showed robust agreement, but some details differed. At 27 nanoseconds, the integrated values were significantly more negative than predicted. The measurement was also sensitive to unwanted correlations between probe phase and signal transmission, so the team performed systematic checks.
Then the strongest conclusion is the sign-changing trend and broad agreement, not perfect agreement at every point.
Correct. Now, what does negative excitation time mean?
It can't mean an atom stayed excited for minus several nanoseconds on a normal clock.
Right. Tau t is a post-selected weak value inferred from the correlation between probe phase and transmitted photons. Quantum interference can make that conditional average fall outside the ordinary range, including below 0.
So it is not an ordinary residence time, but it is tied to an observed phase shift.
Yes, the atom's weak response tracked the same negative quantity identified as the transmitted light's group delay. The lesson is not that physics has opened a route into the past. It is that a quantum system's conditional history cannot always be described as a classical sequence with positive durations.
The final selection changes the question. We aren't averaging every incoming photon. We are asking only about the subset later detected in transmission.
Exactly. In ordinary statistics, selecting a subset can change an average. Quantum interference goes further, allowing the weak value for that group to become anomalous.
And the experiment did not infer the anomaly only from when the outgoing pulse arrived.
That is the advance. A separate, off-resonant probe monitored the atomic medium itself. Its phase shift changed sign where theory predicted a negative group delay, linking optical timing to a weak measurement of atomic excitation.
How should we read future claims about negative time?
What observable was measured? How weakly was it measured? Which final events were post-selected? And is the number an ordinary elapsed time or a weak value?
That keeps the results strange without turning it into a time machine headline.
It also captures the significance. The experiment tested a precise model of light interacting with matter and showed that a negative weak value can correspond to a measurable physical correlation.
So the surprising answer came from asking the atoms, not merely watching the clock.
Yes. When transmitted photons were selected, the atom's own weak signal said that the relevant excitation time value could be less than 0.8 femtoseconds.